This is lecture number 9 in our course of practical program analysis. A little recap. So we already talked about how we can formally describe the program, how we can describe the semantics of the program, how we can describe the syntax. Then we also talked about how we can do some sort of analysis, the data flow analysis and symbolic execution, in order to try to reason about the program, to predict what may happen during the execution of the program, where could be the bugs and how can we find those bugs without even executing the program. And we discussed the difference between the static analysis and dynamic analysis. You remember that static analysis is when you just look at the code, look at the text of the program, but you don't run it, so you don't need a real hardware to evaluate your code. And the dynamic analysis is when you actually run it and you see what happens when the program gets executed on the real hardware, and then you do some analysis to reason about some properties of the program. For example, you can say whether it's possible to get an error exception, for example, division by 0 in real execution. So you can reason about that without running the program, or you can try to run, maybe simulate, not because if you really run it on production, then it's not anymore testing. It's not anymore within the scope of this course. It's something different. It's like bug detection on production. But we're talking about analysis of the code before it goes to the real user. Then we can decide whether the division by 0 will happen. And in order to do that, we also run the code. For example, we do the unit testing. So we write the tests which simulate the behavior of the program in real code. This lecture is about model checking. Model checking is, in my opinion, even more complex than data flow analysis and then symbolic execution. We're moving step by step from a less complex topic to a more complex. So data flow, in my opinion, was the least complex type of analysis, and symbolic execution is more complex, and model checking is even more complex. And I have to say that I'm not an expert there, so don't take everything I'm going to say today for granted. So you better check it yourself how it really works, and I may make mistakes. So I will just explain you now how I understand model checking, and I will show you a few practical examples of how I tested it and what results did I get. So a few words about what it is, and then we go to real examples. So model checking is when we, in theory, we are trying to, let me give you an example first. You will understand what I mean. So actually this is the structure of the lecture. So we start from motivating example, then we go to the theory. So now you see I tried to give you the theory, but then I failed. So first I'll give you the example, then we will discuss the theory, how it looks in theory of model checking, how people formulate all of that, and then we go to model-less. That's my name, model-less model checking. So there's going to be model checking, but without the model, and then some links to the literature. So there are not a lot of material today, more like discussions and analysis of what you're going to see. So let's start from the motivating example. Division by 0, our favorite case. So take a look at the slide you have in front of you. There are two functions. The first one is called the measure. Here it is, measure. Another one is called roll. So on the first one, look at the left one, the process number 1, a measure. So measure is doing, it is taking the external variable, which is global. So there are two global variables for both processors. The first one is x, the second one is y. So the function measure is checking the value of the variable x, and if the x is not equal to 0, then it sets into the variable y 1 divided by x. So it's pretty simple code, and this is the control flow graph for this code. So we start from here, we check if x is not equal to 0. If it's not equal, then we go here, x, and then we say y equals to 1 divided by x, and we basically finishes here, so that this line is missing. And we can also, of course, continue this way. And then what's interesting is that we go back here. So I expect this process, for the sake of argument, just for this discussion, to run endlessly. So imagine that the left process, number one, just goes, without stopping. It's just over and over again doing the same thing. Imagine this is the real software. Of course, it's not a real program, but imagine it happens. So it has an external two variables, and the only thing it does, it just takes the x, does this calculation, and then stores the result into the y variable. The process number two is, take a look at the right side, it's called roll. So what it does, it just increments the x, and then if x is more than 10, it just deducts the 10. So if you run this process, only this one, again endlessly, again making the loops over and over again, then it's going to basically increment x, and it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 11, and then it's going to be again 1. So it's never going to be 0 in this case. So we're never going to set 0 into x. Am I right? So this is pretty safe. These two processes, this one and that one, they even can work in parallel. So that's the whole point. So they can work in parallel, and we assume, we don't know how they're going to interact, but we know them individually. So individually, they look for us pretty good, pretty safe. So we see the control flow graph here, and we see the control flow graph there. And again, this is the line here is missing. So they individually, the analysis which we know, for example, the symbolic execution analysis, we can apply to the first graph and say, is it going to happen that that's going to be the division by 0 in this statement? And symbolic execution will tell you, no, it's not going to happen. So no matter how much you analyze this left control flow graph using symbolic execution, using data flow analysis, all the techniques which we studied so far, they're not going to give you any result, because they're going to look, individually on this graph and on that graph. So it's going to be two separate programs. And there is no way to combine them together. We cannot anyhow create, I don't know, maybe it's possible, but we cannot create one program which we can then give to symbolic execution and ask what's going to happen there. Ask for the qualities, for the properties of this program. So I'm just showing this to formulate the problem. Why do we need model checking? Because there are certain situations, and mostly these situations are related to concurrent execution, to parallel execution of two or more processes. And when they work in parallel, then no other analysis techniques which we studied before, they can actually do anything good. They cannot. So we need something else. So we need somehow, and if you look at this and at these two processes, they actually are pretty safe the way you are. So if you I'm thinking now, because if you run them together, then actually there will be no problem, because this guy, the second process, is not going to set x to 0. So there will be definitely no problem here. So even when they run parallel, there should be no problem. The problem will show up, and I will show you now how this will show up. If we, actually I was not thinking about this, now I'm thinking about this. So probably the trouble will show up if we say here, instead of more than 0, instead of this, we say that. So if I replace this sign with the more or equal to 10, then in this case, it will be possible to see 0 assigned to x in this line, right? Because if it's equal to 10, then with just x minus 10, and 0 will be set there, and the bug will have a chance to to show up there. And even in this case, there is no guarantee that we will definitely hit the problem there. So if we just run them together, just imagine you take this code and put it into compiler, C compiler. You can do it. You can just compile these two pieces of C code and then run it, and you will see that even if you use more than this sign, more than x is greater than or equal to 10, then it's also not a guarantee that you will see the problem there. Sometimes it may not show up, sometimes it may. So probably, I believe that most of you understand concurrent programming, right? You understand this, the problems which are coming from programs written in or executed in multiple threads or in multiple processes. So they look okay. Individually they work, they're solid. If you just run one process or you run another one, then they're just perfectly safe. But the troubles, they start when they interleave, when they do things together. So this is what we need model checking to do what symbolic execution cannot do. How they do it? So model checking, again, I'm continuing the example. I'm working with the same piece of code. So I combine them together. You see now I have the program which combines these two processes together. So the idea is that we can take this program and then create another program using another language. This is C language, or C or C++. And from this language, we move to another language, which is called ProMela. This is the name of the language. The language which is designed not for writing real programs, not for creating software which will be used by users, but it's the language which is created in order to model another programs. So this code on the right is a representation, let's call it an abstraction. We already know this word. An abstraction of the code on the left. So this is the real code which goes to the CPU. So this is the chip. And we put this code on the CPU and it works. This one never goes to any CPU. This code is only for the analysis. So the question is how you can move from the code on the left to the code on the right. So how you can model your logic using the instructions and constructs and the instruments of the language on the right. Why do we need this language on the right? The language on the right is good for analyzer, for the special software, which will look at this code and will say, you know what, if you run this program on the left, if you run this code on a real computer, then there is a chance that you will get the division by 0 in this line. So there is a tool which only understands this language, which only understands the model. So we take the real code, we model to this language, and then we move this language to the tool, which we're going to discuss right now. So we give it to the tool, and the tool will tell us, now I understand what's going on there, and I understand the meaning of this code. I don't understand C, I don't understand Java, I don't understand your languages. I understand my language, and in my language you describe to me how the processes interact. And we can take a look how it's done there. It's quite simple syntax. It's much more simple than the languages you know, than Java and C++. So look, they define two processes. They say proc type, this is the keyword for the process, the first one, the second one. Inside this process we say do means the endless cycle. So we start the cycle and then there goes the condition under which we can enter the cycle. So we say true, so we always enter the cycle. So do, it's an endless loop. Then we say if and phi. If and phi, this is the forking. And then we say if x not equal to 0, then we don't do the division, pay attention. We don't do the division here. So these instructions, we just say some variable dbz, the variable dbz, which I call division by 0, I set it to the Boolean value if x is equal to 0. Why I'm doing it this way? Why I cannot just say float here, like I did there, and then set the float y? Because I did integer for x, and I don't do float y. Because this language, this ProMela, it doesn't support floating point numbers. So all it supports integers, booleans, arrays, something else. So there's a very limited set of things. And why not floating point numbers? Because they want you to describe everything in a very deterministic way and very independent from the hardware implementation. Because that's what they say in the documentation. Because floating point numbers, they vary. They could be different from platform to platform. So that's why they say no floating point numbers, only integers. And then I use Boolean, so I put the Boolean in here, and I just set it to true if the division by 0 will happen here. So you see, I'm not really interested in actual execution of the code. I'm not actually interested in what's going to go into the y variable. It's my model. It's not a real software. So I throw away things which I don't care about. So I don't care about the actual value to be stored after the division. All I care about is whether the division by 0 will happen. So that's why I made my model, so I simplified it in this point. That's why it's called abstraction. So I throw away the details which are not important. And I stay with the details which I care about, and I do care about understanding whether the division by 0 will happen or not. And there's another interesting thing. So if you look at this operator if, then you see that there are two branches. Well, usually we have if, then else. But here it's a little bit different. So if, in their case, in this language, may have multiple branches. So it could be if this, and then this, and then this, and then in the traditional programming language, say C++ and Java, we have if with only two branches, if and else. They have multiple. It's more similar to the switch or the case operator in C and Java. So they say if x not equal to 0, then you go there. Otherwise, skip. So what it means here is that you see the skip stays in the place of a condition, not in the body. So this is the condition, and this is the body. You see here the body is skipped. But actually, if we skip the body, it means that the body is also something like that. So you see the skip stays in the condition part. And that's interesting to notice. What happens when this modeler, when this execution of the model gets into the code, it jumps into the first condition, and it tries to evaluate that. And if it can evaluate that, if it can evaluate it to true, then it goes this way, calculates this statement, and goes away. If it cannot calculate, for example, if is not equal to 0, and it says x is equal to 0 actually, let's say x is equal to 0. In this case, it will try to find in the list of conditions, in this list of branches, it will try to find the next one which calculates to true. And if it cannot find any of them, it will stay in the if forever. So if is a blocking operator, let's put it this way. It tries to enter one of the branches, and if it cannot, it just holds and waits until it can. So that's why if you remove this line, that was like a mistake. I hit myself. So if you remove this, which would look for you like more the traditional way to write if statement, then this block will be stuck at this point, and it will never continue. So it will wait and wait and wait for this condition. So you have to specify two alternatives for the if, to go left or to go right, or to go another one. There could be more. There could be more options for the if operator. And once one of them is true, then the if will continue. That's just for you to understand that this language is actually the language for modeling concurrency. It's not the language to write what you write in C and C++ and Java. It's a different language for different purpose. And here again we model the role process. So again the endless cycle, do and OD, and we do x plus 1 if. Here we're pretty much the same. Here I didn't reduce the functionality. Here I reduced the functionality. I simplified it. Here I didn't. So that's the way to prepare my program, my software, for the analysis. So I wrote it in C++, now I created the model, and the model is written in the language, and my next step is to give this model to the tool, and the tool is called Spin. Spin stands for Simple ProMela Interpreter. So this software is quite old. It was created a long time ago in a government project of the United States, and then they made it open source. So it's quite old stuff, but it is on GitHub right now, and it works. So you can just get it from there, compile. It's pretty small. It compiles in a few seconds, in maybe half a minute, and then you have the binary file, the binary executable. It's called Spin, and I give this code, which you saw already. So I give this code to the Spin, to the computer, and I actually added this. I don't know whether, yeah, I didn't have it there, so I added this line here. So you see that this language actually can do some normal stuff, not only be a model for processes, but also do, printing to console and doing some maybe other operations. I'm not a deep expert there, but I know that printf definitely works. So when I run it with the Spin, I say Spin, and then I give the name of my file, and I put this line here, because if I don't do that, it's going to be a very long, basically endless line of endless log of lines, which go x equals to 1, 2, 3, 4, 10, and then you continue. It's going to be x equals again to 1, x equals to 2, and so on and so forth. It will go forever. If you run it this way and you say tail here, then it will never stop. So it's going to be running and running and running. There is no tail, because there are no bugs, because there will never be division by 0. As we saw before, because we have this operator here. So if I change it to this, then definitely it will stop. But when I was preparing this slide, I missed that case, so I made it a bit more complicated case. So I created I propose you to consider another situation now where I change our code a little bit with this modification. So I put this this instruction to the language. It means, you can guess, it means run this process in 2 threads. Not in 1 thread, but 2 threads. So run them parallel. So in total there will be 3 threads. 1 thread here, and 2 threads over there. That's what I did. That's the modification. And on top of that, I put the monitor process, an additional process, additional thread. So it's going to be 1 thread, 2 threads, and the thread number 3. So it's going to be another thread, 1 thread here. And this one will do exactly, now you understand the syntax, so you can guess easily what it's going to be, what it's going to do. Again, the endless cycle, and 2 assertions. So it says, assert that there is no division by 0. So these 2 guys, they will run endlessly, and this one will watch them. It will also run in parallel, and it will check if the division by 0 is ever set to true. So we don't want to set it to true ever. So we say don't make sure that this dbz variable is always false, and make sure that x is always more than 0. more or equal to 0. More, it's again my mistake. So it should be just more, right? So we want to check that. This is, it's just a simulation. It's not a real case. Unfortunately, I'm showing you something which is very academic. So just for the purpose of analysis, let's say we are interested in these properties of our program. We are interested that the division by 0 doesn't happen, and we are interested that x is always more than 0. And we want this thread to be executed in 2 parallel threads, this process, this algorithm to go in 2 parallel threads. So now we run it again. So we take this program, now this is our program, okay, and I give this program to the spin tool. Now let's see what the spin tool says. So again, this is my program. On the left, which, as you saw before, has exactly the same, not functionality. It's a model, so it's maybe not correct to say that there is a functionality. The right way is to say that it is a right abstraction of the functionality, of some functionality. But now, as you can see, it's not only the abstraction. So this is the abstraction of the functionality, and this part is, as they call it, we're going to discuss it a bit later, but they call it requirements for the abstraction, requirements for the model. So this is, again, the model, and this is requirements for the model. So we require the model to behave this way. And now we go to the spin tool, to the model checking tool, and say, could you please confirm that the model goes along with the requirements, so they match each other. And the tool will tell us if we did the right model, and if we wrote the right requirements, if we did the right job here and there, then the tool will give us the output, which looks like this in my case. So look what happened. I say spin, then I give my ProMela script, and it says error, assertion violated. Assertion violated on line 22. So I believe line 22 is this. And it says the 4 processors. Remember, we had 4 threads. So it says 4 processors. And it gives us the state where it failed. So the assertion failed, and the state of the program, of the evaluation environment. And you remember the state, usually it's just the full collection of all variables and their values. So here we say x was -9 and division by 0 was, and dbz was actually 0. So we violated this assertion. This assertion was violated probably earlier than division by 0 happened. So I guess you understand why the division by 0 happens and why -9 we can get there. So look what happens. This is usually the source of all troubles, of most troubles in concurrency, is when we write the code. Let me scroll back a little bit to the original code which I wrote there. So when I look at the code here, then I naturally, here. So if I'm an average programmer who is focused on this particular piece of code, and I expect everything to happen according to my expectations, then I understand that if I check x here, and I know that x is not equal to 0, then I use it here. But I don't think, I forget about the execution, the evaluation, the opportunity for other threads to do something here in between. So here, this one may happen between these 2 lines. So when programs run parallel, when threads, they go parallel, then their statements, they get interleaved, and they are not executed like this, like all my statements and then all your statements. They go in parallel. So my statement first, and then your statement, my statement, your statement. And that's how they go. So I need to expect that if I do something in one line, then it's not a guarantee that what I found there on the first line will still be true on the second line, because something may happen in between. And that's basically the main source of all troubles in concurrent programming. And that's why people use synchronization, so-called. So developers, when they don't know how to solve the concurrency problem, like here, for example, like how do you solve that? So they just make this block synchronized, the entire block. So they say, using different instruments, maybe locks, maybe the synchronization keywords if they exist in the language. So they just make the entire block synchronized, and they say, make sure that the block is synchronized or atomic. That's another quite popular word. So atomic means that whatever you see in my block here, all of these instructions, they just been executed together and nobody can interfere with me. So my execution is solid. So basically it means that when I start the execution, I just tell all other threads, please stop. So when the execution is atomic, it's basically a signal to the thread manager who is deciding which thread to use. We're just telling them that please stop this one or many others, all other processes, all other threads, they must stop and wait until I finish. In this case, I'm pretty safe. In this case, I have like an isolated environment, which is atomic execution. So nobody can inject anything in between. But of course, it's expensive, because in this case, we'll lose the whole idea of concurrency. Because in this case, we are, if there are more hardware resources than just one single CPU, one single processor, then the software which is doing these atomic things, which is explicitly informing and instructing the virtual environment or the operating system to stop and give full control to me until I finish, then in this case, all the available CPUs, which could do something useful at the same time, they just stop and wait. And that's really ineffective. So it's better to design software the way that it is that it doesn't have these blocks which are atomic, or maybe such blocks, they exist in the software, but the amount of them or the size of them is as minimum as possible, as small as possible. So large atomic blocks or large functions or large methods which are synchronized, so-called, it's a bad design practice, bad programming practice. It's better to find a way how to design them without synchronization, without this atomization, but at the same time keep them safe. Make sure that they don't fail, like in this example. Because this example, again, if I replace it with this more unequal and then run them in parallel, then definitely at some point of time this thread will set x to 0, and this thread and that may happen right between these lines. And if it happens right between these lines, then boom, we have division by 0. So getting back to the output of spin, so why I just backtracked a little bit and explain you the motivation for concurrency is to make sure you understand why there is number -9 here. So how come x became -9? Because we had two parallel threads. So this role is being executed in two parallel threads. So they do it in parallel. So the first one is checking x, it increments the x. Another thread also increments the x. So they do it in parallel at the same time. This one makes x plus 1, and this one makes x plus 1, for example. And then this one checks if x is more than 10, and the answer is yes. And then another thread at the same time checks if x is more than 10, and then also the answer is yes. And then they both together, they do this. They do -10, -10. So they basically, from +10, they jump to -10 and then again to -10. So they go into -9 or -10. It's unpredictable exactly what's going to be the number, because they already in the in the conflicting execution flow, because they're not atomic, so they use the same shared variable x, and each of them believes that they have full control over this variable. And the problem, of course, is in this statement. So this comparison goes first and decrement goes next. Between these two statements, anything can happen. And when it happens, it's already not true. So I check it if it's more than 10, and here another thread already did some manipulations, and it's already not more than 10, it's already 0. But I'm saying, no, I still want to decrement it by 10. So it's inconsistent. I get into inconsistent state right here. Why it's inconsistent? Because it's not consistent with my expectations, how I understand it. So my expectation is that x satisfies certain conditions. So that's what the spin is for. That's the example for you, the practical example. So basically you write the software, then your software fails on production, you don't understand why, then you take this software, you carefully design the model. So you take the programming language, special programming language, you write the model in this language. How you do it, it's a separate question, but you write this long, very complex model, and then on top of the model you design the requirements. You say, this is my assertion, so this situation should not happen, that situation should not happen, and then you give it to spin. So what spin does? Spin basically is trying to execute your model in all possible scenarios. So it's not going to be just one execution. It will try to run your model as long as possible, as long as necessary, in order to go through all possible situations which may happen with your state. So all the possible values of your variables, it will try to jump between them and see what happens. You can do the same with your real software, and you skip this modeling and skip the requirements, but it will be just longer. So you can create a unit test, of course, for your original program. For example, for this one, we don't need this spin and everything. We just take this code, we just put these two guys together and run the unit test and wait for a few, I don't know, minutes, for a few seconds. It depends. In this particular example, we're going to wait for a few seconds and the error will blow up, definitely. But if the example is more complex, if the software is larger, then maybe you're going to wait for a few minutes or maybe a few hours before the actual conflict between your threads will happen. And maybe you will not even see it. I mean, you can wait for hours, and only in production server you will see it. So what do you do with that? For this, the spin can help you. You model, you design your model, and then on the model, spin will not, you know what the beauty of the spin is? The spin will not go on the same pass again. When you run your unit test, it will go through the positive pass, without the error, multiple times, millions of times, until it gets to the negative pass, to the pass which has an error. This is how your unit test will behave. Your unit test will just run millions of times before it hits the error. Spin will just go once through the positive way, and then it says, okay, that's enough. I know what happens in a positive scenario. Now let me try another state, let me diverge from the default scenario, and let me see how it's gonna what's gonna happen if the state will be different if we have the conflict. So let's not get into too much details now, but just understand the idea that there are more paths in your code than just this one. First, second. There's just pass 1A, B, C, and D. But if you put these two control flow graphs together, if you interleave them, then there will be more paths. There will be more alternative sequences of execution. And spin will go through all of them fast, much faster than your unit test, in which case you need to wait. Okay, that's called model checking. Classic. model checking. That's not actually the theory, it was the practical application, so you can see what it does. Now let's see the theory. The theory is much more complex, and we're not going to discuss all of it today. It's too much, but let me just give you the idea. So the theory says that the idea of model checking is this. There are 4 steps. Well, actually 3 steps, but step number 4 is just to wrap up the big picture. So they say the model checking is a method for checking whether a finite state model of a system meets a given specification. So exactly what I showed you before. So we make a finite state model. Finite state means that it's not infinite. It's not something that has infinite number of states, but it's a model which has a number of states. So the model is in this state, then in another state, another, so it moves from state. Each state is basically a collection of variables, of a collection of values for all state variables. So in our case, the state variable is x and y. So state number 1, x is 0, y is 0. State number 2, x is 1, y is 0. State number 3, x is, and so on and so forth. So all of these are states. And the system can move from state to state. X is 0, y is 0. Then we say x, so this is, for example, state number 1. X is 0, y is 0. State number 2. X is 1, y is 0. State number 3. X is 2, y is 0. And then we say, okay, the system moves from state number 1 to state number 2. From state number 2, it can move to state number 3. From S3, it can move back to state number 2. And this is a full set of transitions between states. So we say model checking is a method for checking whether a finite state model of a system meets a given specification. For example, we can say my specification is this. It never goes to state number 3. Never. That's my specification. So I want to make sure that the system will never come here to here. Never, never, never. This is the forbidden state. So what I do to do this, model checking can help me to check whether a finite state model meets my specification. So whether this software which can be modeled like this will never reach state number 3. Or for example, I can say never reach state number 3. Or I can say from state number 1, it will always go to state number 2, and from state number 2 will always go to to state number 7, something like this. So I want this to happen. So when I meet state number 2, I want to be sure that always the sequence of states after S1 will always be this. That's my requirement number 2. This is my requirement number 1. Never in state 3. Requirement number 2. When you see state 1, go always to S2 and then always to S7. Then I don't care what happens. That's my requirement number 2. It could be another requirement I can say, for example, requirement number 3. I can say, I don't know, we will see. In the next slide, we will see the combinations of these requirements, how you can specify them. So basically, the workflow is this. First, you represent the software as a model. We did it before. Second, you define constraints or maybe requirements, the same, on the model using temporal logic. We will see now what I mean. So this was just the example of temporal logic for you, but very primitive. Number 3, evaluate the model until constraints are violated or met. So run the model, evaluate the model, see how it behaves from state to state, from state to state, according to the logic of the model, and observe. Observe what happens. And if you observe this, you say, wow, we met this requirement. Very good. If I observe S3, at some point I say, wow, they violated, R3 is violated. That's all I need. Violated or met. So I say R2 was met, very good. R1 was violated, very bad. And I give this information to the user. That's the point of model checking. Just tell the user what I see. Tell the user that, yes, I saw that. I was running, and I saw this combination of states. The user may say, thank you very much, because it would take me a few hours to actually see it in production. but you did it in a few seconds because you tried, because you are specially designed piece of software which knows how to evaluate the model. And finally, when you see the output, when you see the so-called trace of execution, then you can refine the model, refine the constraints, and go over again. That's how the software developers, they use these tools for model checking. They just run them again and improve the model, modify requirements, again run it, again modify the model, again requirements, in order to debug. It's sort of a debugging, sort of the mechanism of finding bugs. And it is, as you can now understand, it is more like a dynamic analysis. It's not really a static analysis, as you see, because we actually run the code. Even though we don't run the actual code, but we run the model. So we need the software to somehow be executed. So usually people classify model checking as dynamic analysis of programs. And then we go to, let's see the example. This is more complex stuff than I can explain in one lecture. So I took this picture from the really good paper. You should read it. It's not really big. It's called Model Checker Spin. It's the paper from the author of this tool. And I just made a screenshot from the paper. Don't get into this. It doesn't really matter right now what is said there, but just look at the syntax. So this is the model which, using the same language, ProMela, which explains how this machine behaves. So from this state, it moves to this state. From this state, it moves to this state. So these are the states, and these are transitions between them. And then another machine explaining another language, another piece of specification, model. So this is the model, and this is the model. And they explain the behavior of this machine. And then look at the command which is being executed here. This is the most important part. So they provide the formula here. So this is the formula in the temporal logic language, sort of. On the next slide, I will show you this language. So it's a language which they invented in order to describe the requirements. In our previous example, in the motivating example, we were not using any language. We were just doing assertions. I was just saying, assert that x is more than 0. It's quite primitive way to define assertions. It's very straightforward, very primitive. But if you want to say something more complex, like I showed you before, for example, you want to say that after S1 we go to S2 and then I go to S7. So this sequence of states, I need some special language to explain that. I need to say somehow to the spin tool or to any other tool how to catch this situation. So how do you do it? How do you say, if you see S1, then you expect S2, and then you expect S3. You need some formalism, you need some language to define that. And people invented that language. And this is where they use this language. So you can look at the syntax of the language. So this is the operator of this language, this is another operator of this language. So basically the language is this, then P, U, and Q. This is the formula of the language which they use in order to say what they want to say. And on the next slide, I will show you what they want to say in this case. So it's called, there are a few temporal logic, there are a few approaches to formulating what I just mentioned to you, to formulating such statements like for example, always after you enter this database, then after that there should be some file deleted on the disk, something like that. So these two events, they always should go one after another. If this happens, then I should see that one happen afterwards. Or for example, if I see this happens, I should not see that one ever happen again. For example, if the user says delete my profile, then I should never see any attempts to download any data from the user profile down the road during the execution of the program until the program stops. So how do I explain that? I have to say, if the user says delete my profile, then no events of that kind should show up. And this is the linear temporal logic operators, you see, which people introduce. So for example, this operator says, for example, this one. So I can say, for example, again, I may make a mistake, but let's improvise. It's not so important here. So let's say I say a user, this is my event or something like event number 1, which means that the user says delete my profile. And I say delete my profile, and then eventually has to hold. Eventually, there should be some negation, I believe. Let's say something like this, not event number 2. And event number 2 means that we print user information. So this is my formula in linear temporal logic, which says exactly what I just told you intuitively. If the user deletes, don't print their information. And this is the operator. Okay? And this is, I believe, the operator these guys were using here. But, you know, because here it's just graphically this way, but on the console, you can type this. It's better to type this one. But I may be wrong. Maybe this is a representation of a different operator. Maybe of this one, for example. So temporal logic defines a language in which you can talk when you specify requirements. You define the model using some ProMela, whatever language. Then using this language, you specify requirements. Then you give it to the machine, and machine using some magic inside. We're not going to discuss this magic today, that's for sure. It uses some magic inside. It returns you back the result. And it says, yes, you know, actually the user deleted the profile, but then you printed the user information, your software. So I analyzed your 5,000 lines of your code, of your model, and yes, it happened actually. After the deletion of the information, blah, 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 the user did something and then something else, and then recreated the profile, and then something happened again, and boom, you printed the user information, and the event 2 happened. So actually the real flow of event was this. It was E something, E7, and then it was E5, and then it was E1, and then it was many E, and then it was like, 10 minutes of work, and then suddenly E2. So the machine found, look, E1 is here, and then E2 is there, and this is exactly what is defined by this requirement number, number 7. So it says it will give you this combination, and it will print it to you on the log, and it will say, hey, I spotted that, I found this correlation of the events, which is exactly what you were asking for, so think about it. Maybe it's a bug, I don't know what you wanted, but I found it for you. Well, that's model checking. It finds events happening in certain combination for you in your model. Okay, and the last part of today's lecture is, as I understand it is, it's model-less model checking, which is a simpler approach, because what I showed you before, it's quite, in my opinion, complicated. So it's going to take you a lot of time to learn this language, how to describe your model, and then the language of this linear temporal logic, which you also need to learn, you need to understand many things together, and how you transfer your software to the model. That's a complex task. There is another approach, which, for example, is implemented in the tool, which I will show you just now. But before we go into the tool, let's discuss again another example. Let's consider another example, which demonstrates so-called race condition. You probably know this definition, race condition. We kind of had the same right now discussed, but this is more clear example. So race condition is when there are 2 threads, and one thread is supposed to reach the point faster than another thread. But then in some, according to some circumstances and in some situation, another thread actually reaches faster. So they compete for the resources, and at some point of time, one thread is faster, another is not faster, and the error happens. Look at this code. This is Java. So in this Java code, we have one static variable integer, which is 42. When the program starts, it's number 42. And then we do two things. The thing number one, we start a new thread. So those of you who are Java programmers, do you understand what's going on? So we start a new thread, and in this thread, I set d to 0. And then on this line, I print x equals 2, and I do the division. 420, I divide by 2. So if I remove this from the code, then everything will be just fine. Every time I run my program, it will just start, it will divide this, and it will print x equal to 10, right? That's going to be the output. However, if I have this thread, then it may, before I reach this point, maybe this instruction will be executed faster, but maybe not. Maybe yes, maybe not. So we don't know in which state the system will be when it comes to this point. Maybe x will be equal to 0, or maybe x will be equal to 42. So there are two possible states, state number 1, state number 2. I don't know in which state will the system will be when it comes to my statement where I do the division. And nobody knows. It depends on multiple factors, and it's impossible to predict. This is called race condition. That's why they say is the condition of where the system's substantive behavior is dependent on a sequence of other uncontrollable events. So there are many other factors which we cannot control. And if I run this code, look, I compile it first, and then I do while true, this is bash command. So I do while true, do Java race, and done. Java race is, I start a Java virtual machine, and I give this class file race, which runs. And look what's happening. It runs it, it's okay, no problem, it's okay, and then boom, here I have the exception. Exception in thread main, a division by 0 at line number 9. And again, okay, and it will run forever until I click Control-C, until I stop it. So out of 1, 2, 3, 4, 5, 6, 7, out of 7 executions, 1 out of 7 is error. And it's very lucky if I have 1 out of 7, because in reality, in practical problems, it's not going to be 1 out of 7 million. Because 1 out of 7 is easy to detect. You just run it and you see the error. But if it's 1 out of 7 million and then the users just report it to you, and you cannot reproduce it locally, you cannot repeat it on your development environment, then it's a problem. So this is called race condition. And now let's see how can we detect this race condition using the tool, which is, before we go to the tool, let me show you exactly what I just said to you, the states. So look at this code again. You saw it, and now see the graph of the transition, the visual representation of states and transitions between them. So first we start the program here, and then we move to the state 1. In state 1, d is equal to 42. From here we can move either to print, in this case everything will be fine and the program will finish, or from state 1 we can move to state 2. If the thread gets, first gets faster to us before we get to the printf, we can be moved, the system can be moved to state 2. And in state 2, d is equal to 0. And from state 2, we have only one way, only one road, is to failure. So this is our picture of the states, how the system can move. How did I build this picture? How did I draw this diagram? Intuitively. I just, using my intuition, because the code is very simple, very, very primitive, I just use my intuition and I can draw this picture. If the system is much larger, then my intuition will be not enough to do that. I will not be able to to draw such a diagram, such a, an easy way, a fast way. That will take me much more time, or maybe enormous amount of time. And there's a problem called the state explosion problem. So if the system is even more complex, and if there are loops, for example, and if there are longer algorithms, then the number of these states, state 1, state 2, it's going to be state, I don't know, 10 million. It's going to be a huge number of states in which the system may happen to be. And the more variables I have, and they're called state variables, so this D is the state variable. Now I have just one state variable. And because I have just two assignment operators, I assign to 42 and I assign to 0. Because of that, you can multiply and you can see I only have two states in my software. But imagine I have two variables. Imagine I have 10 variables. And imagine in each variable I may potentially have dozens or hundreds of possible values. So how many states? It's a multiplication of these numbers. So it's going to be the numbers could be extremely huge, and the graph will be enormous, and that's called state explosion problem. So they just explode, and then the question is, how do you analyze that graph? What would you do with that? Because in this graph it's quite easy, and I'll show you right now how the software can analyze this graph and can actually detect the bug in this software. But when it's more complex, state explosion is sort of a problem which difficult to solve. There are some approaches to solve that. There are some solutions which can reduce the amount of states, which can reduce the amount of states for the analysis. We cannot reduce the actual amount of states which exist in the software, but we can reduce the number of states which we analyze. So let's use the tool which is called Java PathFinder. Java PathFinder is the tool which takes this code, this one, just like this, just this code, without any models. So I don't need to draw any model. Forget this modeling before, forget the requirement specification. I just take this code in Java and I give this code to the tool, to Java PathFinder, and it gives me this output. Just two parts, so it's a long one, but we probably gonna read it, it's not so complicated. So this is how I give it to the tool. You see? I just say Java minus jar, this is the jar from, it's called jpf.jar, also open source, so you can download it, it's quite small, quite easy to configure. So you run this jar file, you give this jpf configuration file, just a few lines which says take my Java from there, and then it runs it. And in the end it says there is an error. This is basically the part which says there is an error. So it says precise race detector. So this one is the one that detects the problems. And you see it says D equals to 0, and it understands that the reading is happening there. It doesn't say that there's going to be division by 0 here. I don't see this message. But that's because I'm not probably very, familiar with the tool. From what I see is that it complains, and it should take some time to decrypt the output, to understand what it says. But basically it says that it understands you see that it says the transition 0, transition 1, transition 2, transition 3. So it found the way how the system was transited to the state where the problem happened. So how this software works. It takes the Java code, actually it takes the byte code. It takes the compiled Java code, not the source code. It takes the compiled byte code. It has an internal virtual machine. So it's not a real virtual machine, but a fake virtual machine, internal, which is probably more simplistic than the real virtual machine. And using this virtual machine, it tries to execute your program step by step. And when it executes it, it understands what is the graph of your states. And it tries to go through your states as minimum times, as little times as possible in order to go through all possible states. So this is the goal of this software. The goal of it is to go through all possible states. And pay attention to this output, which is very interesting here. Look, it says search started. You see? Search started. And then, after the search started, we see this message. So actually, it means that the first printf, the first command x equals to 10, actually worked. So it did print 10. And then it did it only once. So it successfully went through a successful pass with no errors, once. And then when it tried to find a different direction, then it hit the error. So remember how many times it took me here to detect the problem. You see, I did it 1, 2, 3, 4, and then the number 5 there. And I told you, this is the simple software. If the software would be more complex, that would take me, I don't know, 1,000,000 times. I would have to go 1,000,000 steps, to make 1,000,000 steps there before I reach the exception point. They, in this Java PathFinder, they didn't do 1,000,000. They just did once. And after the first one, it immediately understood that it's time to go to the second one. It's time to find the alternative path. And that's the feature of this software. To find the first path, and then try to find the second one, try to find the third one. So all the possible transitions between states, this software is trying to find. Without the model, without your requirements, it just goes, it just traverses the graph of the states, and then you can configure it by attaching some listeners, by attaching some additional modules and plugins, which will, when the transition happens, it will do some observation. It will analyze, okay, what's going on there? Should I stop? Should I report the bug? Or we can continue traversing the graph. So this Java PathFinder is quite popular for Java community and quite useful. Because, like I said, because it's easy to use. You don't need to invest your time into modeling, into requirement specification. All you do is just take the compiled software, compiled Java code, and give it to it. But the software must be executable. So there has to be the main function, and this Java PathFinder has to understand how to start it. So it actually starts it. It doesn't do that. It's actually dynamic analysis, the real dynamic analysis. It executes every line. When it meets something which goes to some native code, some complex operation with the files, and something which is dangerous, some maybe network operations, it doesn't do it. It just skips it. So it does what it can do. But it's not a real Java machine. It doesn't really evaluate your code, and doesn't really, it does evaluate, but not in a real way, not with the real outbound connections, as far as I understand. So it is reduced functionality. It's reduced power of the virtual machine. There are alternatives to these tools. You can find them. Just Google for model checking. But that's what I wanted to show you. And here's my final slide. What about ChatGPT, which we love these days? So let's see how ChatGPT actually deals with this problem. So I asked ChatGPT this question. So I gave this software, which we just analyzed with the Java PathFinder. So I asked the question, so what do you think about this? So this is the piece of software, which you saw before. The question is what it is, and the answer is, yes, there is a problem with this Java code. So ChatGPT understands there is a problem. And then it says, the issue is that the code is creating a new thread and updating the value of the static variable inside that thread. It's exactly what's happening. At the same time, the main thread is trying to access the value of D to perform a division operation. So this is very accurate description of what's going on. And then it says, since the main thread and the new thread are executing concurrently, there is no guarantee that the new thread will finish updating the value of D before the main thread tries to access it. If the new thread updates D to 0 before the division operator in the main thread, the code will throw a division by 0 exception. It's a very, very good explanation of what happened. Without any model checking, without any Java PathFinder without any execution, any dynamic analysis, anything. It just looks at the code and just explains what's going on. Like I told you, it's magic, so we don't understand how it works. But however, in this case, ChatGPT makes a mistake. So now this ChatGPT is making a suggestion how to fix that. And the fix they introduce is wrong. So take a look. To avoid the issue, you can use synchronization or locks to ensure that the updates to D are completed before it is accessed in the main thread. Blah, blah, blah. So it is suggesting, this is the solution which they suggest, which absolutely will help nothing. Because they are just putting the synchronization on this code and synchronization on that one. But this is not the problem. There is no synchronization. There's no need to synchronize anything because synchronization will not help. Because the setting to 0, this one may happen right before this block of code. So we can set it to 0 here before the division will happen. So the actual solution to this problem is not the synchronization. It's probably well, I don't even know how to solve this right. So maybe the best solution is to move this code before the thread. So now so don't start the thread before the printf operator. So first you do the printf and then you start the thread. But if you want to do the thread first, then in this case you probably need to I don't even know what's the right solution. Anyway, so ChatGPT is wrong in this case. It suggested something which is not going to help anyhow. But of course, the description of the problem was absolutely correct, accurate, and surprisingly, as usual, surprisingly detailed. So it's not just a line of code with this absolutely difficult to digest output like coming from Java PathFinder, but actually it's a textual description of textual description of what's going on. There you are. Okay, so to summarize, model checking is a powerful instrument for solving problems coming from concurrency. Without concurrency, there is no real benefit. Symbolic execution can do the same job, but I think with more accuracy, with more and easier. Because you don't need to write this model. So like I said, the making the model is the difficult part of the job. Making the model is the most, writing requirements also difficult. You can try it yourself. You can try to play with this spin tool and see how it behaves. Just take a simple program, take a simple software with intentionally made mistakes, the concurrency mistakes, and then make the requirements and see how difficult it's gonna be. But you can probably write your own model checking system, and it's not gonna be difficult. So you can make your own language like ProMela, but ProMela is, it's bigger than what you can do, but you can make a very simple one. You can make very simple language where people can describe very basic things. For example, they can say, this is my thread, this is my another thread. In this thread, I access the variable, and then in this thread, I access the variable, and then here I set the value, here I read the value. For example, that's it. That's the entire syntax. And then you read about this temporal logic, and then using their operators, you can invent again some language, maybe even which even may resemble the language they have for this linear temporal logic, and then you write the interpreter of this language, and then you from the model you try to create the full set of the states, and you probably don't create it up front. You just start running through the model and see which states are showing up and which states may also show up if you change the values here and there. Like if you at each execution point, at each evaluation statement, you diverge your execution to different places. Then the number of states will grow. Okay, it may explode, like I said, but maybe on simple examples it will not explode. You will have a limited set of states, and then you see how you can apply these expressions with the temporal logic for your model. And there you go. You have a model checker. Make it open source, put it there, and see how it goes. But I think that the future and the more usability and more user adoption you may get if you create something like Java PathFinder, if you create something like that, which doesn't need a model, which doesn't need people to create a model. You can make something like this for a different programming language. This is for Java, and it exists for Java for years. It's just maybe 15 years or so. But there are many other languages right now in the market. There are more younger languages which probably don't have such a tool. JavaScript, I don't know, Rust, Go. So think about creating something like this for the languages which don't have it. Because for Java, it's quite convenient. Go to YouTube and try to watch the videos from the conferences where people explain how they use Java PathFinder. You will find quite interesting examples where they say that, hey, we're in production team, we have a web service, I don't know, an online e-commerce website, and we use PathFinder to find problems, and actually it helps us, and actually it finds bugs, and we use it for complex parts of the system where concurrency is of essence, where it's an important ingredient of our success. You can do the same for a different language. Think about it. JavaScript, for example. I'm not sure JavaScript is, it may be affected by concurrency problems, but take some language which definitely has threads and this concurrency with the multiple threads, multi-thread execution, like Python, Ruby, whatever.